This is ECE 341 Random Processes. This will be lecture 7 of part 1. In today's lecture, we're going to cover a couple more topics in chapter 2, mostly independent trials and also some elementary reliability analysis. Once we get past those two basic concepts, we're going to spend the bulk of the time going through some examples that illustrate our counting principles that we've been covering over the past few lectures. Let's deal with independent trials first. The idea of an independent trial is that I'm going to have a total number of times I do something, like n. So I'm going to have n, and all the trials are going to be independent. For this particular case, we're also going to look at each of those trials having the same probability of success, which we'll call p, and the same probability of failure, which is just the complement of the success, 1 minus p, sometimes called q in the book. We'll call successes s, and we'll call failures f. So what do we want to do? We want to figure out the chance of having k successes out of n independent trials. So for example, you might have 10 trials and you want to know what's the likelihood that out of that 10 you'd get 3 successes, something along those lines. A way we could try to visualize this is we could draw some bins. These bins are for each one of the trials. So I go ahead and I lay out n total bins corresponding to those n trials. And what I would like to do is I'd like to fill k of those bins with the letter S to designate a success. All the other ones would necessarily get a failure. So I want to fill in k s's and then have n minus k f's in there. How many different ways are there for me to fill, right, those bins with k s's? Well, that's a problem that we looked at, a counting problem that we had looked at before. The number of combinations, the number of combos, or maybe ways to fill, right, the ways to fill k bins with S's, and it doesn't matter the order that I fill those bins. I could fill the first bin with an S and then the second bin with an S, or I could fill the second bin first and then the first bin second. That kind of order doesn't matter. Just what matters is which bins get it. The number of combinations, the ways to fill those K bins with S's, and you necessarily will get the other ones with the failures. It's just our combination. So we know that that is going to be N choose K. Now, because the trials are independent, we know that the probability of having those k successes and those n minus k failures, that's an intersection of all of those different events. But because it's independent, the intersection of all those events is just the probability of each individual trial multiplied together. So independence allows us to just go ahead and multiply these together. So we would have the probability of k successes, right, out of n trials equals what? Well, we're going to have n choose k. That's the number that have k successes. And when you have k successes, the probability of those k successes is going to be p raised to the k, right? We have k successes each with an individual probability p of success. Because they're independent, we just multiply them all together. And then we're going to have the 1 minus p, that's the probability of the failures, and there's going to be an n minus k of those, so that the total number of trials in there is n, right? P of those, or k of those, are going to be of the success type, so those are the p's to the k, and n minus k is going to be the failure, so the 1 minus p to the n minus k. So that one's a pretty easy one to count out. There's also a section in the book that talks about basic reliability problems. The basic idea of a reliability problem is taking a look at components or subsystems that are configured either in parallel or series kind of configurations. So we're going to have independent components. Again, this is based on an independent component assumption. And for this particular one, to start us out, we're going to go ahead and think of each one of these components as having the same probability of success or working. We're going to again call that P. P would be between 0 and 1. And then there would be the complementary probability for that component or part failing or stopping to work. And that will just be 1 minus p, which we'll sometimes also call q. This would be really easy to modify for independent components that had individual success or failure probabilities. In other words, where you would maybe subscript the p based on which particular element you were dealing with in this overall system. Let's look at the two common configurations we find in engineering. There's a series connection, right? So we put a bunch of systems in series. So you have a system 1 that leads to a system 2 that leads to a system 3. And the only way that you're going to get success out of this cascade of systems is that every single system has to succeed. So when you have systems in cascade, you aren't going to get success all the way through unless you have a success with every single one of those guys. So in the series connection, the probability of success requires that all k systems succeed. Because they're independent, we can just multiply those guys together. And so the probability of success is just going to be p raised to the k, right? The overall success probability, right, depends on all systems simultaneously being operational. And since there's k of them in series, and because they're independent, we just multiply them through. There's only one way to count that, by the way, too. So that's why there's a 1 out front, not a and choose k or something like that, because we've got k subsystems and all of them have to work. So the success probability there, really easy to find. If they were different probabilities for each subsystem, you would just have a product going from 1 to k of the pi's, right? You just multiply their individual probability of successes together for all those ones in series. Another type of calculation or connection that we might look at is this idea of a parallel connection between systems. In this parallel connection, you can get a success out of the system if any one of those k subsystems is operating. And so system 1 could be working, or system 2 could be working, or system k could be working, or all of them could be working, or 3 out of 5 could be working. Any combination that has at least one of those guys working would give me success overall. This is a redundancy kind of approach to system engineering. So you might have heard cases of like flight systems on an aircraft. There are critical systems on there where maybe they have 3 systems operating in parallel. So there's 3 redundant systems to do something like maybe flight speed or knowing the angle that the aircraft is banking. These different systems are done in a parallel kind of connection, right? They're done in a redundant way to help ensure better success probability overall. So if I'm interested in the probability of this entire system succeeding, I'm going to start by looking at what its failure probability is. For a parallel connection, the only way that system fails is if every single one of them fails. So a probability of failure, probability of failure on this guy. So if I go ahead and take a look at the probability of failure on this parallel connection, it's just going to be the failure probability of one of the components, right? And how many components have to all fail? They all have to fail, so that's going to be k of them. Because it's independent, we just multiply their probabilities together. So failure requires all k to fail, which would have probability 1 minus p raised to the k. So what is the probability of success? Well, the probability of success, right, is just equal to 1 minus the probability of failure. We had made this note before that on some cases, it's easier to compute the failure probability than the success probability. There's lots of ways this thing could succeed. It could succeed if one of the systems is operational, if 2 of the k systems is operational, all the way up to k of the k systems operational. And you'd have to count each and every one of those different combinations and get all their probabilities together and add them all up. Much, much easier to do as 1 minus the failure probability. So probability of success in this case is going to be 1 minus, we already computed the failure probability is 1 minus p to the k. Probably the most simple way that we could carry this out. A little later, we will go through some examples of both the independent trials and the various reliability kind of operations, either through a parallel or a series connection that will come probably in our next lecture. Okay, so for the remainder of this lecture, we're going to look at a bunch of different counting examples. For the past few lectures, we've been looking at different ways we can count events. We know if we can get an idea of how many events occur out of a total number of options, that leads our way to finding out likelihoods or probabilities. So part of the reason I separate this from when we actually talk about the different counting methods is that part of the difficulty in counting is just knowing what kind of counting you should be doing, right? What kind of counting method you should be doing. Identifying from a problem statement whether order matters, whether they're sampling with replacement or whatever the case may be. And so I haven't made any assumptions at this point, right? I'm not going to put these in any particular order. We're just going to go through and read some word problems and then work our way to trying to make sure that we can do the necessary counting that is associated with that. Sometimes this seems like a judgment call, but there is almost always a most reasonable approach or a reasonable set of assumptions. You do have to use your judgment, your engineering judgment, when you're dealing with word problems. So let's take a look at this first one. This first example says the following. It says, how many ways are there for an instructor to select, let's say for grading, 2 problems out of 15 that were assigned? So This is similar to how I do things, right? I usually assign 3 problems and then I collect 1 for grading. In this particular case, this used to be the old way I did it. I'd make bigger assignments less frequently, and maybe you'd have 15 problems assigned on that, and then I'd collect 2 for grading. So how many different ways could I select those 2 problems for grading? In this particular case, I don't really care the order that I pick the problems. I could pick to grade problem number 1 and problem number 7, right? Or I could have picked problem number 7 and problem number 1. And in the end, I don't care which of those 2 I picked first, right? So there's this part here where the order doesn't matter. The problem itself does matter. What's the basic counting that we want to do here? Again, it's that number of combinations. So a combination is the appropriate way here. So the number of combos, the number of ways that we can do that is just going to be, I have 15 things and I need to choose 2 of them because order doesn't matter. The order of that selection doesn't matter. So I'm going to have 15 factorial over 15 minus 2 is 13 factorial and 2 factorial. If I go through that and calculate that out, I'm going to have 15 times 14 divided by 2, and that's going to give me 105. So there would be 105 different ways that I could pick a couple problems out of 15 for grading. All right, let's work on another example. This is one that has some origins with your digital systems kind of class. You know that you can represent numbers using bits, so ones and zeros. A common word size for representing digital numbers is an 8-bit word. And I would like to know how many 8-bit numbers have exactly 3 zeros. So for me, when I start thinking about this, maybe a little picture would help me out. I'm going to go ahead and just draw the bit positions, right? So there's an 8-bit word, so I should have 8 slots for bits. So I went ahead and showed those 8 slots. I just need to choose which of those slots, which 3 of those slots would have zeros, and then the remaining ones would have ones. How do I choose this? This is very similar to what we were doing just earlier in this lecture. I've got 8 slots and I'm choosing 3. I don't care which order I choose the slots, I just care that I'm choosing 3 of them. So that is going to be an 8 choose 3 kind of count. That's 8 factorial over 5 factorial, 3 factorial. And if you go ahead and you carry out those calculations, you end up getting that guy being equal to 56. Okay, so there should be 56 8-bit numbers that have exactly 3 zeros. Now, this is a case where you, if you were a little bit patient, could probably count them exhaustively. You could look at all the different number of 8-bit numbers. I think that's worth actually thinking about. How many 8-bit numbers are there? How many 8-bit numbers are possible? No restrictions other than that they're 8-bit. How many 8-bit numbers are possible? Well, I know that I can pick one of 2 digits for this first one, so it's a 1 or a 0, 1 or 2 for the second one, and I keep doing that across, so I'm going to have 2 choices for the first, 2 choices for the second, keep multiplying those out. That's going to be 2 to the 8, which equals 256. Why is this sort of calculation maybe something that would be worth doing? In this particular case, it's probably an easier calculation. It's an easier calculation just to figure out what's the total number of words possible without having that restriction of having 3 zeros. Then when I go through my logic and I find out, hey, I got a calculation of 56, I can do a little bit of a reality check, right? I can sit there and say, is that in the realm of possibility given this upper limit of 256? And in this case, I see that. I've seen lots of cases where students are getting kind of started in this counting process. They maybe picked the wrong kind of method, and maybe they did an incorrect kind of counting, and instead of 56, they got 1,022 or some other huge number. If you computed that upper limit, you would know that there was a problem with your counting because there's no way that a more restrictive case would have more occurrences than the total number for a less restrictive case. So sometimes putting some bounds on the numbers will help you get some sense of whether or not you're doing well. Another thing you could do, and I'll just do this in the margin, right? Another thing you can do is you can reduce the dimensionality of the problem, right? And you could work on that reduced dimensionality problem to try to come up with a method to do the counting, and then you could scale it up. So let's look at a different one. Let's say how many have 3-bit words. So 3-bit words with maybe 2 zeros, something like that. So 3-bit is a lot easier. I know that there's a total of 8, 2 to the 3, 8 3-bit numbers. So there's a 000, there's a 001, there's a 010, there's a 011, 100, 101, 110, and a 111. So those are the full 8 possibilities that I've got. I'm going to go through and I'm going to just find out which one of those have exactly 2 zeros. The first one has 3, that's more. So the second one has 2 zeros. The next one has 2 zeros. This one has 2 zeros, and I keep going through there and I don't see anything else. So I see in this particular case, 3 of these numbers have 2 zeros. If my logic was correct for the other one, right, how would I do this? I would sit there and I'd say something along the lines of, hey, I've got 3 things and I need to choose the 2 slots that have the zeros. What does that give me? That gives me 3 factorial over 2 factorial, 1 factorial, which is equal to 3. And that does match the number that I got on there. So this is also a strategy we can do in our counting. If you have something that is a little bit problematic, right, to write out, 8-bit, you could probably do it. You could write the 256 numbers that are possible in there, but that out of that 256, I don't know, I wouldn't want to be writing that out by hand. So I reduce the dimensionality here. I reduce the dimensionality from 8 down to 3. Pick something else that's kind of similar. Instead of 3 zeros, I'm doing 2. It wouldn't be too interesting to have 3 zeros out of 3 because I know there's only one that has that. And then I test my logic. I test my logic and see if it works out in that smaller case that's easy to enumerate. So that's another strategy we can do. You'll see in all of these cases, I tend to work towards having some sort of diagram, or maybe I reduce the dimensionality, or I do some other kinds of kind of creativity in trying to manage the information and make sure I'm counting things correctly. How about this third example? This third example says a shelf has 7 books. There's 3 different math titles, right? So maybe you have a Calc 1, 2, and 3 book. And then there's 4 science titles. Maybe there's Chem 1 and 2 and Bio 1 and 2, something along those lines. And I'd like to know the number of ways the books can be arranged so that all 3 math books are together. So in other words, you're going to have all 7 books in a big row, right? And I want to see how many different ways there could be such that the 3 math books are always next to one another. This one can be a little bit tricky to count, but I think, again, doing some graphics can help us out. The thing I'm going to focus on in this particular case is that the 3 math books are together, right? Because the math books are together, I'm going to write that as something like an m cubed. Okay, I'm going to treat that sort of as a single thing. I'm going to say that all 3 of those math books have to be together. And then what else do I have? I have a science book, a science book, a science book, and a science book, something like that. I've got those 4 different science books sitting in there. You could subscript those out if you wanted to, or not. For the time being, what do I want to try to do? I have 5 things here then, right? I've got the 4 science books, and then I've got this group of 3 math books, and I'm going to keep it as a group right now. And then I'm going to see how many different ways I can order that group of 5 things, kind of glue the math books together. Well, how do we do something like that? We could certainly do this through like a total permutation on that. We know that the number of permutations, different orderings, permutations of those 5 things is equal to 5 factorial, something along those lines. So I could have 5 factorial ways of moving those guys around. That would allow us to individually identify each of the science books. They're each treated as something separate, right? You've got that science 1, science 2, science 3, science 4. But what it doesn't account for is the different permutations that are within that bundle of 3 math, right? So the number of orderings of our group of 3 math books, right? That 3 math books, which I call kind of m cubed, is equal to 3 factorial. There's 3 objects in there, right? And there's 3 factorial ways to order those 3 objects. So it could be Calc 1, 2, 3 in that order. It could be Calc 1, Calc 3, Calc 2. It could be in that order. It could be Calc 2, Calc 3, Calc 1. And if you keep going through there, there's a total of 3 factorial or 6 different ways. Okay, now I just have to multiply. That's the rule of product. I'm going to just multiply these together. So the total number of ways, according to what was specified here, so that all 3 math books together, we're going to get 5 factorial times 3 factorial. And if I go ahead and I carry out that calculation, I get 720 different ways. There's 720 different ways that if you put these books up there, right, you would find the different books with the math books, all 3 math books coming together. The order within this does matter, right? Because it would matter whether you were looking for Calc 1, 2, or 3, right? You care about that. So the order that you would find those books does matter, which is why I did the permutation type of an idea. All right, let's go to the next example. The next example here is a hypothetical where we're going to let each state have their own competitions to find the very best computer for some event. Let's call it the random processes, national finals, something along those lines. So every state has all the students in the state go through a battery of tests and find the ones who are going to represent the state to go do this competition. This competition, this national competition, is going to allow all 50 competitors, one from each state, right, to compete for a gold, a silver, or a bronze medal. There's lots of these kind of competitions that go on. So we're going to make a couple determinations on this and then think about how we might use these two different determinations or when they might be appropriate. So how many state combinations of winners are there if the medal type doesn't matter? And what does this really mean? It means that I've got 50 states, right? I know that there's 50 unique states, and I know that there's 3 medals out there. And in this first case, I don't really care who is getting what medal. I just care which states are getting a medal, right? So maybe this is like you're going to be sending out a little news flash, and you're just going to say, North Dakota, South Dakota, and Minnesota are the medal winners for the national random processes competition. We aren't necessarily sitting there saying that we care about which state got which medal. So if I was going to go ahead and try to do that, I would sit there and I'd say I got something like 50 different states, and I'm going to choose the 3 medal winners. And I don't really care the order. I don't care which state gets paired with which medal. So I'm using that combination kind of an idea on this. And so if I go ahead and do that, that's going to be a 50 factorial over 47 factorial, right? The 50 minus 3, and then a 3 factorial. And if I go through and multiply those all together, I end up getting 19,600 as the total number in there. There's 19,600 groups of 3 states, right, for which we could get a different kind of winners of these medals. And that doesn't tell us which state got which medal. That's just telling us which 3 states were the medal winners, right? So pretty large number. Probably not one that you would really want to count out, right? Probably not one that you would really want to count out. You could, in this case again, go down and actually reduce the dimensionality of this to something smaller to see if that reduced dimensionality would help you visualize the problem in a better way. For example, you might sit there and say that there's going to be 4 states and they're going to be vying for 2 medals. My logic is that would be 4 choose 2, which would be 4 factorial over 2 factorial and 2 factorial. That gives me 4 times 3 over 2, or that's going to be 2 times 3, that's going to be equal to 6, something along those lines. So if I think of my 4 things, right, there's 1, 2, 3, and 4. And I'm going to be choosing 2 medal winners. And I don't really care which medals they are, right? So I could have state 1 and 2 get medals. I could have state 1 and 3 get medals. I could have state 1 and 4 get medals. That's the only ways I could get it with state 1. And you can't have state 1 get 2 medals, right? Because they only sent 1 competitor in this. I could have state 2 and state 3, state 2 and state 4, right? And again, I don't have to look at things like 3 and 2 or 4 and 2 because I don't care who got what. I just care that state 2 and state 4 were the medal winners. And then I could also get 3 and 4. And you'll notice in that second line, 2 and 3 and 2 and 4, I did not do 2 and 1 because that was already included before. Count all those guys up, I do get the 6, and that does seem to conform. It does seem consistent with the logic I'd done before. So there's an example where I, again, reduce the dimensionality, right? Reduce the dimensionality, something that I could enumerate just to try to help me visualize the problem and maybe test the kind of math I'm doing to make sure it works out all right. If I look at the next one, it says how many state combinations of winners if the medal type does matter. In other words, not only do we want to say which states won, but we want to say North Dakota was gold, right? And South Dakota was silver, and Minnesota was bronze, something along those lines. Well, this is also very similar, except for what? We don't want to not have it where the order didn't matter. So how many different orderings are possible in this? That is a K permutation. So if you remember, we had something like an NK, that was our K permutations. What's the N in this case? That's where order does matter. How many different ways are there for taking from a group of 50, maybe 3 things, like is the case in this? So I'm going to have 50 different states, and I'm going to be choosing my 3 medal winners, right? And I want to find out how many permutations are possible on that. And with permutations, order does matter. So if I went ahead and I did that calculation, I end up getting, in that particular case, 117,600. If you go back to how that NK was computed. The other way you could get this is you could go back to your 50 choose 3, right? We had 50 choose 3. And then what? I know those 3 things can be ordered how many ways? They can be ordered 3 ways. So that should be my 50 choose 3 times 3 factorial, which is just 6. And indeed, 6 times 19,600 does equal that 117,600. right? 117,600 different ways. So if you had to write press releases, right? Press releases for medal winners, just who were in the medal groups versus the medal winners, like the ones who won the medals and also which one won what medal. Boy, I would way rather do this one, that first one, right? You could have your stories ready and do that with a lot less effort, right? A sixth the effort that it would require to pre-guess all the different possibilities, so you could be out the door with your advertisements instantly. So two different cases associated with the same kind of situation, but maybe two different paths to go depending on exactly what kind of counting or whether the orders deemed mattered to whether it mattered or not. Notice that maybe my original stuff, the original description in here, probably didn't necessarily give me enough to do that. I needed some additional information to really decide whether that order was going to be important to me or not. In this example 5 that we're going to do, I would like to go ahead and use countings. We've been talking about different countings to expand the polynomial x plus y raised to the n. We'll look at this, and when we go through it, what we're going to end up with is we're going to end up with the binomial theorem. That's an equation that relates x plus y raised to the n equal to an expansion of that guy. So how might I might think about this? I know the following. I know something like this. Whoops, that's not the one I want. So let me go ahead and erase that and put it back to this pen. I know x plus y raised to the n, right, has something like an x plus y times x plus y times, and I'm going to keep doing that until I get x plus y, and we know that there's a total of n terms in there. So I need to multiply x plus y n times over. And so one of the things I could think about there is that for every one of those terms, I'm going to choose either the x or the y to carry through and multiply by the next one. And I choose the x or the y, and I keep doing that all over until I get to the very last one, and I choose either x or y, something along those lines. So from each, right, maybe from each, I choose x or y, right? And I'm going to let k equal the number of y's, and I'm going to let then n minus k be equal to the number of x's, something along those lines. So I go through and I choose an x or a y. If I count up all the y's that I chose, that would be like some number k, and the total minus that is going to be the number of x's, because you can either choose one or the other. That's it. Okay, well, how many different ways are there for me to choose ky's, right, out of all of these different terms? So the total number of terms here is n, right, and I'm trying to choose ky's, something along those lines. So the number of combinations, as I go through that and choose these different ones, the number of different ways that I could go through to get ky's and therefore also n minus kx's. So the number of combinations of where we had n terms, right, n terms with ky's, and that also means that we have n minus kx's, right? We know that that is equal to n choose k, something along those lines. So if I do that, that tells me the number of times where I have ky's. If I'd multiplied all those y's together, k times over, I'd get y to the k. And the x's, the other ones that were left over, would be x raised to however many times they were there, the n minus k. So I'm looking at the number of times that I have y to the k, and then I had x to the n minus k. How many different times were there? There were n choose k of those terms like that. As I go through all the different possibilities that I could do with that expansion, there's n choose k ways of getting y to the k and x to the n minus k. Now, how many different ways can I choose the number of y's in there? Well, I could have no y's all the way up to all y's. So I'm going to let that number of y's, k, go from 0 up to n. Okay, well, that whole thing has to be equal to that x plus y to the n. That was just my expansion. So I took the expansion, x plus y, I showed it in expanded form. I thought about this as choosing an x or a y. I counted the number of x and y's, and then I figured out how many different ways are there for me to get those x's and y's. Whether the y's all came at the start or all at the end, or they're mixed up in there, I know that's at n choose k. It's like picking those slots again for their position. The order I pick the slots doesn't matter, but the slots matter. So n choose k ways of finding y to the k, and then connected to that, it's just corollary to that, there has to be n minus k x's, and then we need to cover all the different terms that are in there. This is the classic binomial theorem. So if you go Google or go out to the internet or go back to one of your old math books and look up binomial theorem, it just gives you a way of expanding out that x plus y to the n, and it shows it as a sum from 0 to n of n choose k, y to the k, x to the n minus k. And we've derived this, if you will, through a counting logic approach. Again, you could probably pick a low order case of this. You could do something like n equals 2 as an example. That's something that we should probably be able to do. So what would be the n equaling 2 case? That would be x plus y times x plus y. You multiply that together, you get an x squared, right? Plus I have a yx plus xy plus y squared. Those are the two cases where I have one y and one x. The other one has 0 y's and 2 x's. This one has 2 y's and 0 x's. And so what did the binomial theorem say? It says, let's go from k equaling 0 up to, and in this case is 2. There were two terms, so 0 to 2, right? I'm going to have n choose k, and I'm going to have my y to the k, and I'm going to have my x to the n minus k. Break that up term by term. Put k equaling 0. And I should have probably put in there instead of my n, we know what n was in this case. We were looking at that reduced case that I could do. So this is 2 choose k, and I'm going to have a 2 minus k, something like that. So putting the k equaling 0 in there. 2 choose 0 is what? That's going to be 2 factorial over 0 factorial times 2 factorial. That's just 1. So I'm going to get 1 times, and I'm going to have a y, right, to the 0, so no y's, and I'm going to have an x to the 2. Then I'm going to add to that. This is a k equals 1 term. So I'm going to put 2 choose 1. That's 2 factorial over 1 factorial times 1 factorial. That's going to be 2. So I'm going to get 2 times y to the 1, and x to the 2 minus 1 is 1. The very last term in there, when I get to k equaling 2, is 2 choose 2. 2 choose 2 is also give me a value of 1. I'm going to have y squared, and I'm going to have x to the 2 minus 2 is 0. Y to the 0 is just a 1, x to the 0 is just a 1, and I end up with x squared plus 2xy plus y squared, exactly what I had seen before. So again, I can reduce that dimensionality and try to get maybe a more accountable way, something that's easier to do, that I don't have to go crazy. You know, if n was 100 here, you probably don't want to expand that all out by hand. That lower dimensional case can certainly help me through. I also drew some other pictures, right? I kind of did this picture here to help me visualize how I might do some logic related to that counting so that I could end up with a final result. Okay, so let's move to the next example. This example has multiple parts. This is all going to be in the context of some card playing. So we're going to consider being dealt a 5-card hand from a standard 52 card deck. What do we know a standard 52 card deck has? It has 4 suits, right? There's spades, clubs, hearts, and diamonds. 2 black suits, 2 red suits. For each one of those suits, there are the face cards 1 through 10. The one is the ace, if you will, and then there's a jack, queen, and king. So there's 13 things in the face, right? So if I look at this guy and I count the number of faces there, there's 13. And if I count the number of suits in there, there's 4. And I know I could show this experiment, this idea of a standard 52 card deck is the Cartesian product between the face and the suit. So for every face, there's a corresponding suit, right? So the total number of outcomes there is going to be 13 times 4 is going to be equal to 52, or the total number of elements in there. So I'd like to find some probabilities of some different hands that would be common in poker. You don't have to be a poker player, but we'll take a look at some of these just because they're so common. If you want a little more information on these, you just go out to the internet and take a look at each one of the ones that we're going to talk about here as well. They'll do the same sort of calculations. So I got a standard 52 card deck. I shuffle it up. I hand out 5 cards to you, and then we would like to know what's the probability of getting a royal flush in spades. This is the gold standard best hand you could possibly get. Nothing beats a royal flush in spades. If you get dealt this, you've won. You might as well bet the moon on it because nothing out there can beat it. So I'm going to go ahead and show this royal flush in spades as an event. I'm going to call this event A. Event A has the 10, jack, queen, king, and ace. Ace is high here, all in the spade suit. So every single one of those has to be a spade suit. There's really only one way to get this. We know that. So in this particular case, we can take a look at this guy, and we know that the counting on this, right, is there's only one hand like this. There's only one hand like this. One hand like this. And when I count 1 here, notice that I'm doing that order doesn't matter, right? Order doesn't matter, right? Order doesn't matter there. I don't care if I get the 10, Jack, Queen, King, Ace dealt to me in that order, or if I got the Ace, King, Queen, Jack, 10 done in reverse order, because when I get my cards, I'm going to sort them anyway, so I can take a look at what I've got. The order I was dealt this thing doesn't matter. There's only one way that when I'm dealt 5 cards that I can get exactly those 5 cards listed. If I want the probability of A, then I have to do what? I just need to divide that first occurrence, that occurrence of getting that royal flush. There's only one of those that gives me a royal flush in spades. I'm going to take that and divide by the total number of 5-card hands. So how many 5-card hands are there? The number of 5-card hands, and again, order that I get the cards doesn't matter. So that's a combination. That's 52, choose 5. And if I go ahead and I carry that calculation out, I can go ahead and do that. And I'm going to get something like a 2,598,960, something like that. So there's about 2.5 million different 5-card hands that you can get where the order, right? The order that you got the cards doesn't matter. The cards themselves matter, but the order that you got the cards doesn't matter. You sort them anyway. So what's the probability of A? There was only one occurrence that was A divided by this 52, choose 5, if you will. So that's going to be 1 out of 2,598,960. It is a tiny, tiny probability here. It's just not very likely. You're going to have to play approximately 2.5 million hands of poker to be dealt right off the bat a royal flush in spades. Okay, so let's work to some of the less likely ones, but also the ones that aren't going to be as certain to win, right? The next one that is oftentimes talked about is just a royal flush. Royal flush is a 10, Jack, Queen, King, Ace. They all have to be the same suit, but it's not required to be spades. It could be spades, it could be diamonds, it could be hearts, it could be clubs. So we know there's 4 suits out there. Now, once you got the suit, all 5 of those cards have to be those particular 5. We know to get a set of those 5 particular cards, there's exactly one way of doing it, but there's 4 sets to get us that. So I've got the event B, right? And I know the number in B, the number of different ways of getting B is 4 times the number that was in A. And maybe I could do this as NB equals 4NA, right? Because there was 4 suits, something along those lines. What's the probability of B then? Well, that's the number in B over the total number of hands. We'd already computed the total number of hands. And we also know the number of A, that was just 1. So that's going to be 4NA over this N, which is equal to 4 times 1 over, and I'm going to have 52, choose 5, something like that. So that's going to be 4 over that 2.5 million stuff. If you go through and simplify that a bit, you get 1 out of, and it's going to be 649,740, something along those lines. Okay, so that's a way we could compute it. We could compute it based on some of the stuff we'd seen before, some calculations we did before. I think there's other ways of looking at this as well. So let me show a little alternate way. So an alternate way of counting this guy, okay? We could do something like the following, okay? We have those 5 upper cards, and we have to get all 5 of them, right? We need the 10, Jack, Queen, King, and Ace, okay? So of the 5 upper cards, I need all 5. But of the suit, right, there's 4, and I just need to choose one of those suits. So this is something about the face that I need to get, right? And this is something about the suit I need to get. And then I'm going to divide that by 52, choose 5. That's the number of hands, something along those lines. This is a different kind of logic. It will give you exactly the same number. It gives you 1 over about 650,000, so it gives you the same thing. It's just a little different logic, the different ways of choosing that base sequence, then the ways of choosing the suit, right? This one turns out to be 1, this one turns out to be 4, and this one is about 2.5 times 10 to the 6th, right? We've already seen that. So you get exactly what we had seen before. Why do I show this? Part of the reason is because counting is not a single path kind of exercise. There can be many ways, legitimate ways, that you can approach counting in a problem and get the right result. There's also a lot of ways you can count and get the wrong result. So we do need to employ correct practices. People will have different ways of visualizing that, and those different visualizations are fine as long as they get the correct number in the end. If you are working your way through these problems, I really encourage you to give me some kind of language and some description about what that math means, because if you do that, I have a better chance of following that work and giving you some partial credit if you end up getting something wrong. All right, so let's go to another type of hand that you could be done. The ones that we've talked about before, having those royal flush and spades or royal flush, just a regular royal flush, both highly, highly unlikely. You have to play a lot of cards to get those. Four of a kind is also a really dang good hand, but it's certainly a lot less um, uh, rare, if you will, than just getting those royal flushes. So let's go ahead and take a look at what's the probability of getting a four of a kind dealt to you from a 5-card draw. So I'm going to go ahead and look at the event. The event, I'm going to call it C, and that's going to be you get a four of a kind. That four of a kind means what? You have a particular face across all 4 suits. And then you're going to have another card, right? So you're also going to have another card in there. If I wanted to do this, I might do it something like this. I know that there are 13 four of a kind hands. How do I know that? I've got 13 faces, and if I'm going to get a four of a kind, it's got to come from one of those faces, and there's 13 of them, right? So I'm going to have to get either aces round or twos round or threes round or fours round all the way up to kings round, right? Getting 4 kings, something along those lines. And each of those, so there are 13 four of a kind hands, each with what? 48 possible other card hands. So once I know which face, right, is going to give me my four of a kind, well, those 4 pulled out of the deck, right? And I've got 48 left. Any one of those other 48 cards could be added in there, and it's still going to be a 4 of a kind hand. So one way of thinking about this is that the number in C, right, the number of 4 of a kind hands is going to be equal to, you choose the number of faces, 13 times the 48 in there. And if I do that, that's going to be equal to 624. You could think of that as 624 times the number in A. And what I can get then is that the probability of C is going to be 624 times the probability of A. And if I go ahead and do all of that, that's a 1 over 4,165, which I can finally get to some sort of percent that I can get a handle on. That's like 0.0002401. So it's like 0.02% You have to play many thousands of games of poker to be dealt right off the bat with 5 cards a four of a kind of hand. You got to play a lot, but it's certainly possible. There's lots of people out there that play this amount of cards over a year, so it's not so rare that you don't see people get it. There's also another way we could count this, and so let me just show this alternate way. It's also completely equivalent, and it's a completely legitimate way of doing it. I could do probability of C as being something like this. I'm going to have 13 choose 1. What is that? I have 13 faces, and I need to choose the face that is going to have my 4 of a kind, right? And then of the four faces, or the 4 suits for that face, I need to choose all 4 of them. So this tells me the suit, right, or the face. Gosh, let me try to do this. This first one tells me which face am I going to have, and this tells me I need all 4 suits in there, something along those lines. And then what do I have left? There's going to be 12 faces left for the other card because I've already used up every single one for one of those faces, and I've got to choose one. That's going to be for my extra card. And there are 4 different suits to choose from, and I just need to pick one because I'm only getting one card. And then I'm going to divide this by what? The total number of hands, 52, choose 5, something like that. If you go through that and do all the calculations, you get exactly the same thing. Which one's easier? I don't know. I think that depends a little bit on personal preference, maybe just the way your brain's working. Both of them are legitimate ways of counting it. They're slightly different. I'd probably put a few more notes in here if I was doing that as a homework solution. but both of them give us the same number. There are also things, and this is something you should always be doing, there are also things that you can verify by doing some MATLAB simulations. We already gotten a start on that. How about this next one, a full house? Full house is having a three of a kind, and then a pair. Just because of the nature of this guy, right? The pair can't be of the same face as the three of a kind. There's not enough cards for that. So this guy is something that we're going to try to count out as well. So here's one way I could do it. I know that there's 13 faces, right? 13 faces for the three of a kind, right? Each with 4 choose 3. I only need 3 of the suits out of the 4 available, right? So 3 choose 4, which gives me 4 possible suit combinations, suit combos. So if I need a 3 of a kind, right, I could have a 2, right? That's one of the 13 faces. So I'm going to get my 3 2s, and then which suits are used for those 3 2s? It could be like hearts, diamonds, clubs. It could be hearts, diamonds, spades. And you go through all the different combinations in there. There's 4. There's 4 of them because we're taking 4 suits to choose. We need 3 of them. So 4 choose 3, something along those lines. Then for given that 3 of a kind, so with the 3 of a kind, right? We know that there's 12 possible faces for our 2, or for our pair, if you want to call it that, for our pair, right? Each with a 4 choose 2, because I only need 2 of the cards for a pair. And by the way, that 4 choose 3 and the 4 choose 2, the 3 and the 2 added together gives me the 5 total cards that I had in here. And if I do that guy and I compute that out, that's going to be 6, something along those lines. So the total number of full houses, right, is equal to what? It's 13 times the 4, that's the first line up there, times 12 times 6. And if I go through and carry that all out, that's 3744. So 3744 times the probability of A is going to be my probability of in this case, D, right? This full house. So probability D is going to be equal to that 3744 times the probability of A, where A was just a single event. I could do it as 3744 over 52 choose 2 as well. And if I go ahead and carry that guy out, that's like 0.00144. If you compare that to the 4 of a kind, right, that was 0.02%. This one is a 0.1%. So it's at least 10 times, right? At least 10 times, probably approximately 10 times more likely than that 4 of a kind. Full house is 10 times more. So you're talking play under 1,000 hands of poker, you're probably going to see a full house come out naturally, something like that. How else could we get this? I could get it like this. 13 choose 1 to find the face of the 3 of a kind, and then I do 4 choose 3, right? And then I'm going to multiply that. 12 choose 1, that's the face of my pair, and 4 choose 2 is the way to get the suits for that pair, divided by 52 choose 5 is one way of doing that. This last one that I'm going to do in a really different way, and then we'll come up with a way that's probably just a lot easier, but I want to do it this different way to show that there's, again, different pathways to get you the same kind of calculation. So I'd like to find the probability that your 5-card hand has exactly 3 hearts. I'm going to look at what is called an event sequence. So we're going to look at an event sequence. And that event sequence I'm going to call E is being equal to, I have a first heart, I have a second heart, I have a third heart, I have a non-heart, and I have a non-heart. So my event sequence is 3 hearts followed by 2 non-hearts. How many number of hands are equivalent to that event sequence? Well, how many ways are there for me to get that first heart? There's 13 ways. And once I've got that first heart, the number of ways I can get the second heart, because I pulled one out, is going to be 12, and then 11. And then what's the ways I can get that non-heart in there? Well, if you look at a standard deck of cards, there are 13 hearts, so 52 minus 13 is 39. There would have been 39 cards that would give me that non-heart, and then 38 after I'd chosen one of those non-hearts. If I go ahead and do that, that's going to be 2, 5, 4, 3, 1, 1, 2. something along those lines. You can think of this as having two types, right? You can think of this as having two types. There's hearts and non-hearts, something along those lines. If I want to know the total, right, the total in here, so I'm going to say n total, right, and I want to find that n total, I can take that event sequence, but I also know I could have any of the different mix-ups of this. So I could have it as XXHHH, or I could have HXHXH, all these different kinds of things. So the total number here is going to be NE times, well, we could do it as 5 factorial over 2 factorial 3 factorial. That's like a multinomial with two categories, hearts and non-hearts. The hearts, right, was 3 and the non-hearts were 2. So it's just the different orderings of that 5, right, with the two groups, 3 and 2, something along those lines. That's going to be equal to something like 10 NE, right? So I could just take that number up there and multiply that by 10 in there. So that could be something like, you could think of that as being like a heart 1, heart 2, x1, x2, heart 3, and a bunch of others in there. So we're just adding all of these guys up there. So that was done through a multinomial coefficient. So the n total here, right, n total is going to be equal to 2543120. That's the total number of outcomes equivalent to E. But these are countings that I've done where the ordering has been deemed important, right? All of these have been using rule of product, and it had this implicit idea that the ordering was included in there, but I know ordering is not important. So since order is unimportant, and we already, I guess I didn't have to do this, I'm just showing the different ways that we could do here. We know that the n that I'm interested in is going to be more along the lines of this NE divided by 3 factorial, 2 factorial. There's 3 factorial ways of doing those hearts, right? There's 2 factorial ways of doing the non-hearts. And if you carry out that operation, I get 211,926. Okay, so different ways of thinking about counting. This is the one I'm probably going to be interested in because I know I sort these hands. So what is the probability of this event? What did I call it? This event of having 3 hearts. So exactly, right? 3 hearts, the probability of that guy is going to be that total number, right, where order isn't important, and that's 211,926 over, and then I'm going to have the total number of 5-card hands. That was 259,8960. You go through and you compute that out. That is about 0.0815, so about 8% chance, okay? That's about an 8% chance. Here's another way you could get that n. Could also compute n as n equaling what? I have, 13 non-hearts, right? Or I mean 13 hearts, and I need to choose 3 of them, right? And then I have 39 non-hearts, and I need to choose 2. So I could have just done this with combinations. My guess is most people would look at that and say that was easier than going through all this stuff that I did up here. Maybe that one's not quite so happy. But we do end up getting the same number out of that. If you go and do that calculation, you do get, in this case, a 211,926, exactly what I had before. And then you just normalize by the total number of hands. Again, why do I show this? Because different counting strategies, different counting logic paths can be just fine, right? If properly executed. They don't only have to be one particular way. And I think it's really important that we get flexible in the way we count things, because as the problem statement gets more complex, as the number of conditions and restrictions and way the things interact get more difficult, you're going to need different tools in order to count them right. In the end, I would also say that you always are going to want to sit there and do some verification of your answer through something like MATLAB. All right, so this next one, exercise or example 7, is taken from something I used to do in my signals class. And so this one will take a little time to show, but I think it'll be easier to compute. So we're going to consider a solid and key op-amp circuit. So I'm showing what that looks like. Basically, what do I have? I have an input voltage source, and it's going to have an output voltage. So there's an input and output on this guy. This thing has an op-amp sitting in there. There's 2 capacitors and 4 resistors. This turns out to implement a second order filter. I'm going to go ahead and populate this circuit using nominal components that are in my parts shop. Everybody's been up to the parts shop and talked with our parts technician, and you know that resistors and capacitors come and they're described using a base value and then the exponent of it. So you might have 1.0 times 10 to the 0, right? What would that be? That would be like a 1 ohm resistor, for example, or a 1 farad capacitor. You could have 1.0 times 10 to the 5th, right? That would be, well, what is 10 to the 5th? If you do a 10 to the 5th, that's like 100,000. So 1.0 times 10 to the 5th, that would be like a 100 k ohm resistor. You would not have a 100 k farad capacitor, right? That would be way out of line. Turns out the base values for both resistors and capacitors share the same values for the nominal set. They go in a sort of logarithmic scale, so they go 1, 1.2, 1.5, 1.8, 2.2, 2.7, 3.3, 4.7, 5.6, 6.8, 9, or 8.2. And after that, the next value you'd use would be just a 1.0, but that would be at the next exponent level, something along those lines. So there's 11 different base values you can choose for either a resistor or a capacitor. Now, for this particular part shop, I know the resistors and capacitors can come outside of this, but let's call it modest part shop, has a selection of resistors, but not every possible resistor. So they have things like you can get single ohm resistors, and this would be like 10, 100, 1,000, 10,000, 100,000, up to a mega ohm. So this is the exponent of these guys. So 1 ohm up to a mega ohm. Pretty good range in there, and then of any of those base values. Capacitors, no way are you going to get those large values. So you might have things like 10 to the minus 7 all the way to 10 to the minus 11 farad capacitors as being a pretty typical kind of range. We could also take any one of those component slots and leave it open, okay, so just an open circuit, or we could solder a little short piece of wire in there and make it a short. So there's two different values of that. We have 11 different base values. We have 7 exponents for resistors, 5 exponents for the capacitors, and then 2 additional values for an open or short. And what I'd like to know is I'd like to know how many different circuits are possible for this second order Salin and Key circuit. Well, if I look at the number of resistors that I would have, I know that there are what? If I take a look at this guy and I go ahead and count it, I actually think I made a mistake in my counting here. So let's recount this again. So I'm going to do this in a green. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I feel like I'm missing something somewhere. Where did I miss one? Oh, I know where I missed it. I just missed it in my notes. There's a 3.9 in there as well. So if you look at a typical set of base values, there's also a 3.9. So let's go ahead and fix that. That'll make my calculations match better in my notes. And we know then now that we actually have 12 values. So we'll go ahead and get that corrected as we go along. So how many different resistors could we get for any one of those resistors? So the number of resistors that we have to choose from is going to be what? It's going to be the base values, right? There's 12 different base values times the 7 different exponents. That's just the rule of product. And then I'm going to add to that 2. Why? Because you could either leave it open or short. That's just another thing you could choose to put into these resistor slots. They aren't actually resistors, but they would give us unique circuit topologies. So that's going to give me a total number 86. If I look for the number of capacitors I have to choose from, that's going to be equal to 12, the same number of base values times, but I've only got 5 exponents, and they could be open or short. And so if I go through and do that, that's going to be equal to 62. So if I want to know the number of these second order circuits, what am I going to get that being equal to? There are 4 resistor pieces. Each one can be chosen independently, right? And so through rule of product again, I'm going to get the choices for my resistors raised to the 4, right? For any one of the first resistor, there's 86 choices. Then I can have 86 choices for any of those 86 choices for the second one, and so forth. So that's going to be 86 to the 4th. And then I'm going to have a 62 squared because there's only 2 capacitors in there. If I do that, that's approximately 2.1 times 10 to the 11 circuits. even a really modest part shop. It's only got 86 resistors to choose from and 62 capacitors to choose from. This is a sampling with replacement, right? That's how I ended up taking that 86 getting raised to the 4 rather than having it be something like 86 times 85 times 84 times 83. If I pull out a particular resistor, it's not like I couldn't find another one in the bin. There's multiple in there. So we get a gargantuan number, 2.1 times 10 to the 11. All right, so what can I do with this? I could actually cascade two of these circuits to make a fourth order filter. And this is actually what I had my signal students do. I asked them to design a fourth order circuit to carry out a particular function. So how many circuits are possible, again, using this modest part shop, right? I've got two of these circuits, which basically we knew that that second order number, right, that n for a second order, right, was equal to that about 2.1 times 10 to the 11th, right? So the number of my fourth order circuits is going to be that N2 for the first one, and then we're going to multiply rule of product again, N2 again for the second one. And if I carry that guy out and I do that computation, it is about 4.42 times 10 to the 22, a truly staggering number. Why do I like giving this example? Well, in this particular exercise that I used to give, I used to have an online tool where students could, without penalty, submit their design, get feedback on it, and then kind of get a score as to how good it was. And there were some students who, rather than going through the effort of trying to do the analytical design, just thought they'd guess their way to it. So if you're going to just grab a circuit, put it into the program, evaluate it, and then see how well it does and keep doing that, what kind of a success do you think you're going to have in being able to find a good solution? Remember, the total number is 4.42 times 10 to the 22. So this last part is going to maybe help us better understand these people who decided to do a guess kind of method. They thought they would guess their way. The website that I had on this actually would track people's choices or their submissions. So you'd see some people do one submission. They just weren't interested in trying to find better solutions. Other ones would do 4 or 5. They were trying to tweak it a little bit. And then you'd have these people who do just hundreds. They would just be putting in hundreds and hundreds of submissions, trying to guess their way to a good solution. Well, and actually, the website I had would return a solution. It would evaluate it, and it usually took more than a second. So this next part is actually given the benefit of the doubt. Suppose we could evaluate the performance of 1,000 of those fourth order Butterworth or fourth order filter circuits per second. How long would it take to check the performance of all possible circuits? In other words, if I wanted to do an exhaustive search, right, evaluating 1,000 circuits per second, how long would it take for me to go through that entire list and find out which one did the best? Well, if I have 1,000 circuits per second, right, I can just do a little dimensional analysis here. Is my rate that I'm doing in there. What do I want to do? I'm going to take my number, so I'm going to have my number of circuits associated with that fourth order section, and I'm going to say in 1 second I can evaluate 8,000 of those. So that's going to tell me the number of seconds, and then that's probably going to be a bad unit. So let's say that there's 3,600 seconds per hour, and I know that there is 24 hours per day, and there's something like 365 days per year. This will tell me the number of years it takes me to evaluate these. If I did it day and night at the rate of 1,000 circuits per second, that would give me a value of 1.4 trillion years. All of a sudden, this education that you have, where you are able to design circuits only after 19 years of education, sounds like a pretty good deal, right? You're going to get a really good solution out of 19 years of education rather than trying to guess and check at a rate of 1,000 per second, and you'd have to go for way longer than the universe has been around, right? So 1.4 trillion years. A little interesting thing, and I think I'm running out of time on this one, so we'll do the other examples on the next lecture. One of the interesting things on this is I actually had a student who bypassed my web interface in one of the years that I did this. They really wanted to do it. I used to compete in this as well, and so I'd put out my score, and so students got competitive, some of them did, and trying to be able to beat my score. And so I had a student who decided that they were going to do a comprehensive or an exhaustive search. And instead of using my interface, they reprogrammed their own evaluator in MATLAB on their local PC, so not having to go through the web interface. And it turns out they were able to exhaustively search this entire space and come up with a design. And it's one of those ones where they beat my score, and they beat my score handily. So they did an exhaustive search across that number. It does give you an idea of just how incredibly powerful and incredibly fast modern PCs are becoming. I think this was done probably 10 years ago, and I think it still took on the order of hours, if not a day, to evaluate it. Probably it could be doable in minutes now with some of the technologies that we have, but they were able to do an exhaustive search across 4.42 times 10 to the 22 different designs. Crazy. Next time we will continue these examples, and then we'll start some additional new material.